Hello everyone, today we're talking about properties of determinants. This is material from 3.1. So I think I want to start actually with just a warm-up calculation. We haven't seen a determinant of anything bigger than 3 by 3, I think. So let's compute det of, let's do a 4 by 4. So 3 minus 7, 8, 9, 0, 2, minus 5, 7, 0, 0, 1, 5, 0, 0, 2, 4. So it's a 4 by 4. Now, okay, so what did our rule for determinants say? It says that I first pick a row or column to expand upon, and I want to pick the row column that has the most zeros. So, it looks like this guy is my best bet. It's the only one that has 3 zeros. And so what I'm going to do is expand upon that. Now remember, my sign pattern says I start in the upper left with a plus, then a minus, plus, minus. And so what the rule then says is I say, okay, this equals, moving down that column, it's 3 times the determinant of what I see when I cross out the row and column corresponding to that entry. So that's 2 minus 5, 7, 0, 1, 5, 0, 2, 4. And then I have 3 more terms, right, for every entry in that column. But notice it's minus 0, plus 0, minus 0. So that's why I chose that one. In general, I'm going to have 4 terms in my first step, but 3 of them are 0. Okay, so now I go, apply my iterative process, and I go to compute this determinant. Notice now, so what do? I again pick a row column here. Now, you should pick the first column, okay? But just to illustrate the procedure here, I'm going to do kind of a silly thing and pick the, say, second row. So don't try this at home. You should use the first column. But again, just to illustrate the point. So what happens now, the sign pattern becomes, right, there's a plus in the upper left, and this is minus, plus, minus. That's what I'm going to care about, okay? So this will then be 3 times, again, now expanding upon the second row, the first entry will be a minus 0. Then it'll be a plus 1 times the determinant of what I get when I cross out the second row and second column. So that's det of 2, 7, 0, 4. Minus a 5, right, the next entry, times the determinant of what I get when I cross out the last column, second row. So that's 2 minus 5, 0, 2. Okay? So now we've got a 2 by 2, well, two 2 by 2s to consider, but we can do that. So this is 3 times 1 times the determinant of this, which is 8, minus 5 times, looks like times 4. This is 3 times 8 minus 20, that's minus 12, which is minus 36. Okay? So at home might be a good idea to actually go through and do the first column on this next step to make sure you do get minus 36. Okay, so next I want to talk about kind of properties of determinants. I'm more or less going to list these properties today, and we'll justify some of them in the next lecture. But I kind of want to have them listed maybe in one place. So for the first one, I actually want to first define something. So an n by n matrix, we say, is triangular if it has all 0 entries above or below the diagonal. Okay, so maybe some examples here. So if A is, 3 by 3, let's say something like this. Now this is triangular because below that diagonal you have zeros. Of course, you can have zeros above the diagonal. B, something like, you can also have zeros on the diagonal, so something like this. This is also triangular because above that diagonal are all zeros. Actually, another example that we'll make use of a lot is the identity matrix, right? So that has 1s down the diagonal and zeros below and above. So that's kind of, this is called a diagonal matrix, actually. But in particular, it's triangular because, it's actually upper triangular and lower triangular. Okay, so why do we care about triangular matrices? Well, it turns out they're very easy to compute determinants of. So the first fact I want to list here is the following. So fact, if A is a triangular matrix, then the determinant, like I said, is very easy. It's just the product of the entries along the diagonal. And I'm not going to go through a formal proof of this. You can check the book if you want the details. But the basic idea here is, the basic idea is that if I look at one of these triangular matrices, right, and I go to compute a determinant, what I'm going to do is I'm going to first expand along that, say, first column. And what we saw before, right, you only have that one entry that you care about. That's the diagonal entry times the determinant of what you have here. And when you compute this determinant, all you care about are the diagonal entries, because you can, again, expand upon a row that has all but one non-zero entry, all entries 0 but 1. And you continue to do that every time you take a step. There's only one thing that survives, and it's the diagonal entry times the determinant of the next step, which, et cetera, et cetera. Okay, so that's a nice thing. Maybe just to show you the example here. So what's the determinant of this guy? This is the determinant of A is going to be the product of those entries. So that's 1 times 5 times 2 is 10. Okay, so that's all I mean. It's this nice, easy thing you can do. Okay, so some other facts I want to remind you guys of, or tell you in this case, is that maybe the most important thing about about determinants is that it detects invertibility. So A is invertible if and only if the determinant of A is not 0. I mean, this is kind of how we define the determinant. I didn't actually justify this statement, right? So I'm going to say see next lecture for the reason that this works, where we see how row operations affect the determinant. Okay, so that's going to be the theme of next lecture, that we're going to see how, doing our usual row operations, how does that affect the determinant? We'll see that there's a nice way to control that. Okay, so next fact, how do determinants play with transposes? Well, pretty easy to see that the determinant of A transpose is just the determinant of A. And, why is that? Well, just kind of via an example here. If this was my matrix A, what's A transpose? Remember, my first column will be, I take that first row of A and I make it the first column. Second column is the second row, etc. So if you now went to compute the determinant of A transpose, I can pick any, let's say I pick the second column to expand upon. I do my thing. Well, notice that, the second column of A transpose was the second row of A. So I can choose the second row of A and do the, expand upon it to compute this determinant. And I'm looking at the same calculation in both cases. I get the same number. Okay, so the next fact that not as easy to see, but probably even more important, is that determinants also play well with products. So if I take the determinant of a product, I get det of A times det of B. So that's a pretty important fact for us that's going to show up here and there. Let me just do this with a little example just to have something concrete here. I don't know, let's do a little 2x2 example. So if this is A and this is B, right, I'm picking 2x2s because I can quickly determine their determinants. Determinant of A is what? Minus 1 minus 10, so that's minus 11. Det of B is, looks like 0 minus minus 2, so that's 2. What is A times B? Right, so that's it's a 2x2 matrix. So 1, 2, minus 5, 1 times 0, 1 minus 2, 4. What do I get? So the upper left corner is 1 times 0 plus minus 4. Then I'm getting a, let's see. So this is the upper right corner is going to be 1 plus 8, which is 9. Okay. Then I get a, looks like a 2 and a 1 here. And so what's the determinant of AB? It's minus 4 minus 18, which I think is minus 22, right? Good. And that's right, because look at this. The product of those two things is minus 22 as well, and so it works, right? Of course, that's not a proof, but it shows you how it looks in action. Okay, and so the last thing actually I want to do here is that this gives us a nice corollary for invertible matrices. So let me write this here. So corollary of this fact is that if A is invertible, then what's the determinant of A inverse? It's actually just 1 over the determinant of A. So it's the reciprocal of the determinant of A. And let's actually prove that. Okay, so suppose A is invertible. Well, so we know that A times A inverse is the identity, right? So we have an identity matrix, and this is the property that it satisfies. So now let's apply det to both sides. Okay, so the determinant of A times A inverse is equal to the determinant of IN, right? I'm just applying the determinant to both sides of this equation. And then what do we have? Well, we know now that the determinant of the product of two matrices is the product of the determinants. So this implies that det of A times det of A inverse equals the det of IN. Right? Well, what's IN? IN is one, ones down the diagonal, zeros off the diagonal. And so what is this? This is a triangular matrix, so the determinant will be the product of the entries. That's 1 times 1 times 1 times 1, etc. So that's just 1. So now we can solve for the determinant of A inverse. What is that? Well, it's 1 divided by the determinant of A, as we claimed. Okay, so again, the determinant of the inverse of a matrix is just 1 divided by the determinant. And we know, I should say, that this number is not 0 because, remember, if A is invertible, the determinant is not 0. So this actually makes sense. Okay, so like I said, next time we'll justify some of these claims and talk about how row operations affect determinants. See you then.